Okay, so maybe let's get started. So this is going to be a crash course on diffusion imaging, mostly focused on diffusion tensor imaging, but it has really the full breadth all the way to more higher order models as well as connectomics. I'm really doing this for two people, and that's Maria and Andrea. And but when I'm doing this, of course, I wanted to make sure that everybody who's interested can get it too, so I don't have to do this multiple times. And since we're recording this now, that hopefully, is it recording? Yes, it's recording. Since recording this, maybe in the future, anybody interested, they can just look at this. They don't have to wait for this time to come around where I'm making such a presentation. We'll put this on our website so that everybody who wants it can get it there. I'll also put the slides on the website as well. They're not yet there because I'm still modifying them. Well, not the ones for today, but the ones for, of course, for the next ones. And it's going to be like maybe 3 to 4 talks. It's going to start more with kind of like the basics, just you listening, etc. basically. And then later on, we're going to have more hands-on, which you either can join in on the hands-on or not. That's what we all want, you guys. All right. So this is kind of like the overview of the full set of presentations. We're going to talk about, that's mainly today's introduction to diffusion MRI, as well as what are tensors, what are scalars, how do we visualize them, what can we do with them, how we do tractography, as well as then going over to higher order models. And then the higher order models obviously goes back to tractography, etc. So all of this is going to be focused first on tensors, and then at a later time we're going to go to higher order models. Today, I hope that we can cover all the way, including visualization, maybe a little bit of tractography as well. You can see there's a lot of contributors. Some of them know I took their slides, some of them don't. We kind of like very open about sharing these things. The one that I took most of the slides from, which is at the beginning, is Guido Garrett, my former advisor who's currently at NYU. And we actually presented something like this the first time, maybe 10 years ago at a tutorial, and he actually made the first version of this introduction talk, and I've since then updated it accordingly. So first things for the ones who are not yet that knowledgeable in brain anatomy. I always have to do that to my computer science students. So what are we going to be looking at? Well, we're looking mainly at white matter and the fiber tracts that make up our white matter. So our white matter, think of it basically as a lot of cabling, nothing else. There's no function on there, it's just cabling. And very much, if you're a computer scientist, you may be more familiar with these network cabinets. And it's basically like that. That's the white matter, there's nothing else there. And if you go down, you can see these, that's basically these matrix fiber bundles. And each of these fiber bundles are not just a few tracts. Each of these fiber bundles are more closer to, thousands and close to tens of thousands of fibers that make up one of these bundles. Now, standard MRI does not really help us to look at such fibers. I mean, we can see the white matter. This is a T1 weighted image. You can see the gray matter is gray, the white matter is white, but I don't really see on this how things are connected or how fiber tracks run. So we would like to see something more similar to this, where we see locally how do the tracks look like. And that's where diffusion imaging comes in. Now, this is a diffusion tensor MRI image, and it is colored with the local orientation of the diffusion, which goes along with the local orientation of the fiber. So green would be something that goes back, front, back. Here's the front, back. Blue, something that comes out, so top, bottom, inferior, superior, and red would be left, right. And you can see from this already what's the local orientation of the fibers, and we could probably reconstruct what the tracks look like, and we're going to get later to that. So diffusion imaging, this is a a relatively, comparatively new imaging modality. The first time I've heard this mentioned was back in late 90s. That's basically mid-90s, late 90s, that's when it came up. And early 2000s, that's when it really started maturing. It's the higher order models, I think, are still not mature. There's a lot of things going on, but tensor imaging is largely mature at this point. So what we're measuring here is diffusion. It's not active transport. So there's nothing to do with like the blood pumping or anything like that. But it is Brownian motion of water. Those of you may think back, you know, at physics and chemistry, Brownian motion, that's related to temperature. So the higher the temperature, the more, the higher the Brownian motion. So if our body would be at 0 Kelvin, we would not be able to do diffusion imaging because there would be no Brownian motion. Thankfully, our bodies have a different temperature. Also, a side note here, we're not going to talk more about that. You can actually use diffusion imaging to look at the temperature of a body. So temperature imaging can in part use diffusion imaging in MRI. What we're looking here, though, is more at how the diffusion is shaped. So to say whether it's anisotropic, like here, like, or it's more isotropic. This is an example of not human brain fibers, but these are wooden fibers. This is, you know, wood fibers that make up Kleenex. Very much they hack to very tiny little fibers, which is why the diffusion is uniform. There's no preferred direction. Whereas in newspaper, which is much coarser, wood fibers still have their local orientation preserved. And you can see the diffusion, it has actually preferred direction. That's the preferred directions of the wood fibers in the newspaper in that particular example. And that's what we were trying to get at with diffusion tensor imaging. So what is that preferred direction of diffusion in the brain? So through the preferred diffusion, direction of diffusion in the brain, what we're thinking about is that if we're in a place where there's unrestricted diffusion, such as in the CSF spaces, etc., we would have something like an isotropic diffusion, like this. If we are in the white matter, that diffusion is, though, constrained, so restricted diffusion. And the diffusion will be restricted by the membranes, by the local orientation, by how things are packed, or that there's a lot of space that's between the cells. So intracellular and extracellular spaces in the white matter will impact the diffusion. And what we would see in such a restricted spaces as a diffusion along the tract is going to be less restricted than across the tract. That's what basically everything is based on. So with the diffusion, we can see the underlying structure or microstructure of the white matter tissue. And you'll see that in the talk. I'm coming back to that a lot. So this is not actually directly measuring connectivity or tracts, really. What we're measuring is local microstructure. And from that, we're extrapolating a lot of information. And so any tracts we extract from diffusion imaging are not really truly axons. They are a representation of the local microstructure. They may, in large, agree with axons or with fiber bundles, but not with individual ones. Yeah, all right. Now, when we measure diffusion with an MR scanner, we acquired multiple images. We cannot just use one image. It's rather think of it like it's a difference technique where you measure an image with no diffusion, just like this one here. Looks very much like a T2 weighted image. The CSF is bright, the white matter is dark, and gray matter is kind of like in between. This is so T2 weighted, there's no diffusion happening here. Now we're doing the same sequence. This is a spin echo sequence, where we apply the diffusion, where we have a gradient, and during that gradient, we can measure how much the water molecule is diffusing. And that's what results in such a diffusion-weighted image, what you can see here on the side. So where the areas that experience lots of diffusion, they're going to be dark. Now, the areas that are diffusion that are not experiencing lots of diffusion, they're going to be bright. Now, when we're saying diffusion, I mentioned before a gradient. The gradient is going to be applying along a certain direction. So this is diffusion along one space direction. Think of it like that. Now, because the CSF is isotropic, it's like diffusing across any direction. Any of the diffusion-weighted images are going to have CSF dark because the CSF will diffuse along that direction, whichever direction you have. Whereas if you look on the white matter, you have some areas that are brighter and some areas that are darker. So the dark areas would be along the gradient. There would be fibers that are there along the gradient that we'd applied. So you can actually see from the DWI which is the gradient that we applied if you know a little bit the underlying anatomy. This diffusion-weighted image is acquired at what we call a B-value. A B-value, as you see here, it ranges from 0 all the way to 3,000 in modern applications. It measures, captures the way the diffusion is measured. And it very much puts in it a lot of things that may be different across different scanners. So a scanner that has a higher gradient or different magnetic strength, all of that can be, so to say, normalized through that B-value. So that when we say B equals 1,000, whether this is a Siemens scanner with a super strong gradient, or a Siemens scanner with a weak gradient, or a Philips scanner 1.5 Tesla, we can still compare these. So this is a way to help us put things in correspondence. It largely is related to the gradient strength and diffusion time. That also means, since if I go from here to here, the gradient strength is not going to change. This is the same gradient. But what changes is the diffusion time, meaning when we apply the gradient during the scan, we wait longer and longer and longer to measure what happened to the diffusion. That also means, because in MRI, the longer we wait, we lose, the signal. The signal decays exponentially. We actually get exponentially less contribution, which is why, if you look here, it's so much brighter on this end, versus here it gets darker and darker. But on this end, on the other hand, we get more information about the diffusion itself, like more specific information along a certain gradient, more contrast rich about a certain direction we're looking at. So there's a trade-off. You want to have high p-values because that gives us a lot of resolution on the directions, whereas the lower one gives us signal. So you want to have kind of like something in between, which is why nowadays when you have most DTI studies, they operate around this value b equals 2,000. They may go all the way down to 800 to 1,200, because that's kind of like the sweet spot of SNR, as well as good contrast. So now we have all sets of different gradient that we apply, and we're getting multiple diffusion-weighted images, not just one. What we do from these multiple images is we reconstruct a tensor. So a tensor is a simplification of what's happening currently in a voxel. So we have this voxel where we're measuring our diffusion, and now we're approximating it by basically a Gaussian distribution. A simple Gaussian distribution that's also the same as an ellipsoid. And one thing that you can think about is we assume largely when we do that, that there's a single predominant direction. As soon as we have multiple fibers or multiple fiber bundles, a single Gaussian is not a really good representation of what's happening locally. And if you keep in mind, most of the data that's currently being acquired is about 2 by 2 by 2 millimeters. That's a big assumption, because we have literally hundreds of thousands of axons in such a voxel. We're saying they all have to go this largely the same direction. But for certain locations in the brain, that's certainly a sufficient assumption. From anyone, it's not. We're going to get back to that. The basic equation that's used to describe diffusion with a tensor is this Dieskau-Tanner equation, where you have the diffusion-weighted image. It's made up of the baseline image times this thing here, which is the b value times the gradient times the tensor, the gradient again. And so the unknown here is d, which is this tensor. A tensor, to go back to that, is an ellipsoid. It's basically a 3x3 matrix that's semi-positive definite, meaning it only has an upper triangle. It's symmetric. It means it has 6 unknowns. So in order to locally know what a tensor is, we have to have at least 6 diffusion-weighted images to measure those 6 unknowns. And what we get out of those 6 unknowns, we would fit this tensor, and then, because this is kind of like an ellipsoid, you can think of it that you have 3 directions, which are the 3 eigendirections of the tensor matrix, as well as 3 eigenvalues, lambda 1, lambda 2, lambda 3. The lambda 1, 2, and 3 would tell you about how much diffusion is happening, and the eigenvectors would be telling you along which direction the diffusion is happening. And so if we, in an ideal situation, 6 DWIs would be enough if there's no noise, if there's no any error in our data. But of course, as you can see from these images, they're rather noisy. They're not as nice and high contrast rich as a T2-weighted image. And because time is expensive in an MR scanner, usually we're trying to get our imaging close to the SNR border that's kind of like allowed, which means we have quite a bit of noise, quite a bit of error. So that's why you usually nowadays never acquire just a 6-directional diffusion scan. That's not enough to reliably reconstruct the tensor, just because of the noise and the error. Mother sequence, it's probably a minimum of 20 to 30 directions if you want to do diffusion imaging. And if you want to, diffusion tensor imaging, if you want to do something more higher order, I'll talk about that later, that's closer to 45, 60, or even 100 directions. So we have now not just 6, but in this particular case, we have 15 gradient directions. And so along all these 15 gradient directions, we get 1 DWI image. This is visual visualization of what these gradients would look like. You have the baseline image, and based on this, you're now solving a linear equation system. And there's, of course, many different ways you can solve this, but this is a standard linear equation system that needs to be solved. And what you end up from that is this tensor matrix, where you could actually visualize these individual components. If you're using FSL to reconstruct the image, it will actually write these images out like this, rather than as a tensor image. You can tell it to do a more modern representation, which would put all of this into one image, which is what we usually do when we process the data. But the old style would actually be, you would get a DXX, DYX, and so on. This is basically just a local representation of, on the per voxel level, what the tensor is. So this is the that we computed. By the way, if there's a question, please interrupt immediately. Yes?
Are there any measures of error in the approximation to the image from the tensor approximation?
Yes. So depending on what you use here to do that estimation process, there's the procedure can give you back errors or how those errors were corrected. The tool we're using, for example, DTI-STIM, detects incorrect tensor situations. Largely that is due to negative eigenvalues. So it's a semi-positive definite matrix, so all eigenvalues should be positive. Now, what if your estimation tells you, well, it's actually a negative eigenvalue? So you could either say, all right, it's just a bad tensor, or you can correct it. Most of the tools, such as FSL and our tools, will give you the option of just giving you an image where the tensor is bad, or actually correct it. The easiest correction is just setting that area to a 0 tensor, so that lambda 1, 2, and 3 are all 0. Or you could find the closest possible tensor that's a valid tensor that's as similar as the tensor that's otherwise computed. The place where the tensor estimation usually fails if there's an error is the lowest eigenvalue. The first is usually not a problem. Second and the third can get issues. And usually it's only the third that gives you problems. All right, so here I have also 3 situations of what the tensor could look like. So the tensor in this red area where it's in the CSF, isotropic, so we kind of like have a spherical distribution. So the tensor would look like a sphere. Lambda 1, 2, and 3 are the same. In areas where you have a very tight distribution of the fiber bonds, so they all go the same way. For example, in the corpus callosum, everything goes left to right, which is why the tensor would look very elongated. Lambda 1 is thus large, and lambda 2 and lambda 3 are both small. And then you have areas where we have crossing fibers, so where our assumption of a single Gaussian distribution breaks apart. Now we have 2 fiber bundles. What you can see there is that you get, in this particular case, you have 2 major fiber bundles. You get this more flat disk where lambda 1 and lambda 2 are relatively high. That's because we have 2 fiber bundles, and it's in that plane of the 2 fiber bundles where this disk is. And in the plane out of the 2 fibers, that's where you would have still a low value. That also tells you if you have 3 fiber bundles, 3 large fiber bundles that need to cross at a given voxel, you're going to be ending up at something that looks like a sphere. So you will not be able to actually see whether you have 3 crossing fiber bundles or you have a simply isotropic diffusion. You will not be able to differentiate the 2 just by looking at the shape of the tensor. Of course, if you have 3 fiber bundles, usually you have a pretty restricted diffusion, meaning you have low amounts of diffusion, whereas in the CSF you have high amounts of diffusion. So just by looking at how much diffusion there is happening, usually you know whether you're in a CSF situation or in a multiple crossing fiber situation. So tensors are now this 6-dimensional thing that we humans, apart from looking at locally at tensors, really have not, at ellipsoids, really cannot understand easily or interpret intuitively. So rather than having an image now of these ellipsoids, what we're usually doing is we're taking this and mapping that into a single scalar map, where we have just standard, brightness, grayscale brightness that captures a certain aspect of the tensor. And the 2 major things that we want to be able to capture is, well, the different size of a tensor, whether the tensor is large, whether it's small, maybe different orientations, which is very important for tractography, where we want to go through, as well as different shapes, so whether it's very elongated or very isotropic. And so when we're thinking about mapping out tensors to scalar maps, we're thinking about capturing this shape versus size aspects. And for measuring the tensor size, because this is there's not just one way to do it. Of course, multiple things have been proposed. And as it's usual, it's basically whoever comes first gets to claim the field, and that's usually the one that survives. So there, you see here, you could look at kind of like the length, the average length of the diffusion. If you take lambda 1, 2, 3 and you divide it by 3, or you could look at the area or the volume. What actually is used is this mean diffusivity, which is this number 1. So when we're talking about mean diffusivity, it's not the volume of the diffusion that we're measuring, but rather the average diffusion across any direction that we're measuring. That's also the trace those of you more mathematically inclined, of the tensor matrix. It's often been, and that's why these two things are often used interchangeably. Trace or mean diffusion. Yes.
Do they ever use the determinant as a size limit?
This is the determinant is the volume. If you look at the more mathematical papers that are not in the clinical journals, they often use this, or particularly used to use this. Nowadays, it's very rare to be seen. But yes, it would be a good measure.
Is there any benefits versus, like, I mean, obviously there wasn't enough because it went on later.
Yes, well, it's more, there's a benefit when you're looking at multiple measures. There's some of these measures that we extract of size and shape that are orthogonal to each other from a mathematical perspective, and some of them are not. So theoretically, it would be good if they're orthogonal so that when you analyze them, they're not highly correlated or anything like that. So mathematically, there would be an advantage of one versus the other. That's not how the field works. It's kind of like, it's like that who claims it first gets to go, and now everybody started using this, so now we have to continue using this, which is why everybody's using mean diffusion. It's a decent measure, it's not a bad measure. I plug this one in here because you'll see still in the field, particularly in older papers, you see that often, that there's a misnomer that people use this word ADC, or apparent diffusion coefficient, to mean mean diffusicity. That's not the same. An ADC, and you see that often used correctly too, really is just the diffusicity across one specific direction. And so mean diffusicity is the trace of diffusion tensor. ADC does not relate to the tensor. So is basically is model free. It doesn't assume that we think about the diffusion in a certain way, but just says what's the diffusion along, let's say, the XY direction, the XY gradient, the X gradient in the scanner. But yeah, make sure that you don't confuse these two. Then, so now we have something that captures kind of like the size, how much diffusion is locally happening. The other one that's used a lot, and it's very important, is this shape, basically. Something that represents the local shape of the tensor, whether it's elongated or non-elongated. That's FA, fractional anisotropy. If you look at papers, that's the main thing that people use. Again, this is kind of like a first come, first serve claiming. And what you can see here, it basically relates the differences of the eigenvalues, lambda 1 to lambda 2, lambda 1, lambda 3, lambda 2, lambda 3. So their differences to the total sum of them, and just as a square perspective. And so that means if they're all the same, you already see up here, this is going to go towards 0, so FA is going to be 0. So meaning a isotropic situation is going to be all 0. That's what you see here at the top of this pyramid. So if you have uniform diffusion, FA is 0. Now, with increasing FA, the shape gets more and more different between the eigenvalues, but it's non-unique. So each one of these lines actually represent the same FA, but obviously you can see the shape is not the same. So keep in mind that FA is not unique to a given tensor shape when you're looking at FA images and when you're interpreting FA images or FA values. But one thing you can definitely see is that it gets sharper and sharper the higher FA goes. And it is most sharpest when lambda 1 is much larger than lambda 2, and lambda 2 is much larger than lambda 3. That's the nice thing about this is it's scalar independent, so you can just increase the size of your tensor and it will not change. So it's invariant to size changes. So here we see two such images, standard images. This is in FA. This is a diffusivity image. And you can see that they look very different. They really capture very different aspects of the underlying microstructure. The mean diffusion is high in areas like the CSF. It's a little bit higher in areas like the gray matter, and the white matter is kind of like the lowest area. But it's nowhere really zero. It's not, doesn't really go fully away. Whereas if you look at the FA is near zero in anything that is fluid, so like the CSF, and it gets very bright in areas that are where all the tracks are very tightly aligned, where we don't have crossing fibers, where we have maybe high myelination, and such things like the corpus callosum. Usually that's the areas where we see very high FA values. Another thing is that you can see here, these are skull strip images. One of the reasons for that is if we would look at out here an FA image, it would look rather ugly because there's no diffusion happening there. It's basically all noise. And if you remember, if you look back how this here looks, that's a ratio. But if you get close to 0 with 0, you're going to have problems. Obviously, FA is very poorly defined when our tensor basically gets small and we have hardly any diffusion happening. In addition to these two mainly used properties, we're also computing two more properties, axial diffusion or parallel diffusion, and radial diffusion or orthogonal diffusion. Consider them like size measurements, but size measurements that only focus on part of the tensor. The axial diffusions only focuses on the diffusion along the major axis, so the main diffusion axis, so lambda 1, and radial diffusion focus only on the other two. And these measures here are really related to white matter, so that when you think you're in a location where you have a strong fiber bundle, lambda 1 captures the diffusion along the white matter fiber bundle, and radial diffusion captures the diffusion orthogonal to that bundle. That's the idea behind these two.
That's good.
Yeah.
How is that major axis determined?
So the major axis is the eigenvector. The first eigenvector gives you the major diffusion orientation, and lambda 1 is how much diffusion is happening along that direction. So you take your tensor, you solve an eigensystem, you get 3 eigenvalues and 3 eigenvectors. That's the same as the ellipsoid that describes that matrix. Here I plugged in an example of a mouse study to understand what these measures mean locally with respect to the microstructure and how they affect. I've just picked out one of these, but you can find actually a fair share of such studies online if you do a PubMed search, where in different settings you may want to know what's happening to these values and what does that mean for the underlying microstructure. In this particular case, what they did is that it's a rat study where on one side of the spinal column they made an incision and actually cut part of the spine here and didn't cut the other side. So now we have a direct inherent control where one side should not be affected by anything that happens to this intervention, whereas the other side, obviously there's going to be a strong effect due to that surgery that was done. And these are kind of like these are the images 3 days after such an axototomy. The T2 image, you can't really see much yet at it. On the FA, you see the FA is starting to be lower. The AD is definitely much lower, and the RD is a little bit impacted. Now, let's get to the meat of this paper, and I'm not going to go in detail over it, but it's nicely what they show here. So these are different animals that are sacrificed at different times after the intervention, either 16 hours, 38 hours, 3 days, and so on. And then for each of these animals, they then took slides and they stained them with a myelin stain. as well as with neurofilament stain to see how that intervention affected these two parts and how that correlates with the diffusion scan that was taken of the image of the rat. And one thing that you can see is if we look at the FA, just looking at the FA over time, the contralateral side is kind of like staying stable at a certain value, whereas it takes nearly 38 hours to see something happening on the FA. So diffusion imaging, particularly if you just look at coarse FA measures, is not very sensitive. It's going to take a while until you see an impact on something. So this is not something that you probably want to use for simple functional imaging, even though some people sometimes try to do that. I don't think we have the SNR to do that. And it kind of like drops down, stabilizes, and then drops down again. Now, why is this two-step process? Well, if we look at correlation with measures from the myelin stain and the neurofilament stain, you can see that there's on the neurofilament stain, it kind of like goes down, and then, oh, this is 8. 8, you can see it kind of like goes down, but then straightens out. Nothing more happens. Whereas on the RD, you see this two-step process where it kind of like first gets worse, so it gets higher diffusion, and then there's a second step here. Why is that the case? Because RD much more correlates with what's happening with the myelin. So in this particular case, myelin at 3 days, you see here is not impacted. The two sides look exactly the same, but after 3 days, you see demyelination happening. So RD is capturing much more that demyelination process. But not just. Obviously, it's impacted also by this loss of neurofilaments, which you see more or less immediately happening following the surgery due to the inflammation that's locally created. And so you can see in this particular case with this intervention, AD very much correlates with loss of neurofilaments, whereas RD more closely goes along with myelin degeneration. And the FA kind of like captures both because it's a mixture measure. Yeah.
But then why is it so important to have FA if you have RD and
Well, so RD, so this is a pretty severe thing that was done here, this surgery. If you look at standard studies, RD and AD often not sensitive enough for us to see something. FA, because it's a ratio, is more sensitive, as well as it can be affected by multiple things, multiple processes that usually go in the same direction. So you have a compound effect that you wouldn't have necessarily in AD and RD. But generally, in order to understand things, you would look at all of them to have kind of like a broader picture. Sorry.
No, that's okay. The other two, it's more normalized, isn't it?
Well, yeah, I mean, FA is normalized from 0 to 1, but I mean, AD and RD have also their corresponding measures. So I think if we think about the cross-subject variance, I'm not quite sure whether FA, AD, or RD is large.
I have a
Yep.
this is a mathematical question. So I think there are a number of tracks that between this is human imaging. So between the age of well, between birth and 1, oftentimes AD increases, but RD increases as well.
The RD decreases.
Okay, well, that's right. That's where.
So you can see here through this effect here, that impact, RD went up and AD went down.
Right. Well, that makes total sense, and then FA would of course go up as well. But if you have a situation where both AD and RD increase, then it depends on the magnitude.
Correct.
As to whether FA is going to increase.
Yeah, the setting where both of them increase usually is a inflammatory setting, where you have like influx of water and other things, and because of that, like a swelling, local swelling of the tissue. So everything kind of like increases. And there, FA may not be the best measure. Really looking at MDs or AD and RD is probably going to be better. Yeah.
Would looking at a ratio of AD to RD ever be useful?
Well, FA is very similar to that. It's not exactly that, but FA captures that mostly already. Right. So that's how much I wanted to talk about tensors and tensor map. Now we're going over to visualizations and how to look at that kind of stuff. So the first thing is kind of like the standard visualization that was introduced by Sumomori, is this coloring by principal diffusion direction. And what that basically is, you have this color sphere that kind of like describes the selects for which orientation are you going to be using which color. So you have left, right, which is going to be red, front, back is green, and up, down is blue. And you can see these visualizations. It does not tell you necessarily whether there's how should I say, a flip in orientations and so on. So if I would actually appear incorrectly identified left and right, basically left and right would be flipped, the color would still be red, but the tensor obviously would be incorrect. It would be incorrectly oriented. So it has limitations to look at this, but it's still, looking at this gives you a first impression of whether how your data looks like. Also, you can get very used to looking at these if the data is kind of like aligned to a more standard space, or if the subject has a very nicely aligned position in the scanner. But as soon as the subject turns their head, let's say a little bit like this, these colors will start looking really strange, because now those orientations, they are relative to the scanner coordinate system. They're not relative to how the patient's head is oriented. So they can look rather difficult to look at. And one thing is, well, they're very nice to look at, and they can give you first impression of how your data behaves. They're of course very much related to our visual system. So our visual system does not uniformly, it's not uniformly sensitive to different colors, and then we have people who may be green-red blind, and then you have lots of this stuff here that's totally looking the same. So our vision is not very good in using these colors for any kind of first either visual diagnostic. So radiologists will not use this for diagnosis because of that. And furthermore, we should never use this for quantitative analysis. So I've reviewed paper where people took these RGB values and started analyzing them. And well, those are the easiest paper for me to review because I can just write reject. And so this is really just for quality control purposes if you look at that. As well as when you're doing investigative tractography, let's say you want to maybe get a tract. Where is the tract located? Oh, of course, this can help you find it because like these two areas right next to each other, they have the same FA value, but clearly they have very different orientations. So if you're interested in a front-back tract, like a superior longitudinal vesicle, so you want to track within here. And if you're more interested in a internal capsule tract, you're going to be tracking here. So for tractography, having this visualization definitely helps. Another way to visualize data is to use local glyphs, where it actually display the tensors. If you do that in a 3D sense, the way it's done here, it becomes very disoriented very quickly because you just get to see too much. But looking at these on a slice can be informative whether your data is correctly oriented. So I mentioned before that you may have a left-right flip in your data. If you look at this tensor visualization, you'll see it immediately. Another thing that people often do is rather than looking at the tensor, they look at just the principal orientation. So they see a line for the orientation for the main diffusion direction. And that's usually sufficient. Many of the tools that you can find for diffusion imaging can display these kind of glyphs. Here you see the same glyphs now shown on, not in 3D, but shown on the slice. And the color here is the orientation. So this is not FA, it's just the orientation. And we're taking this part of the image and just blow it up. And you can see here multiple things. You have these areas where the tensors are very elongated, or it's probably in single fiber situations. And you have these areas where you have CSF. You can see here these tensors are all isotropic and rather large. And then you have areas where they're crossing fibers, where you can see these more flat disc-shaped areas, things. And because you can make some really cool images, computer science graphics had for a while was really interested in diffusion tensor imaging because they found cooler ways how to display these. So this is by the way, the corpus callosum you can see here. This is the single tract. I don't think it looks cool, but it's anatomically really very helpful to study. I don't think so. All right, so much about the visualizing the tensors. Most of the times when you're going to be visualizing tensors and looking at them is for the purpose of quality control. And so that gets us over to the whole issue of quality control in diffusion imaging. And I've mentioned at the beginning that SNR is not very good for diffusion MRI images. So DWI images are noisy. Not just that, they're rich with artifacts that can happen. They're very susceptible to motion artifacts, and as well as pulsatile artifacts from the blood, etc. As well as they're sensitive from a geometric point of view to the basically to air interfaces. So the sinuses, which are close to our brain, they create an artifact, a susceptibility artifact that distorts the geometry of these images. So it's very artifactory, it's very noisy. So there is very much an importance on the QC for diffusion imaging. And while the field has moved to better QC, there's still a lot missing in the area. Thankfully, FSL came out last October with a new version that does not a QC, I wouldn't call it QC, but does an automatic detection of artifacts and tries to correct them. It's version 5.13. There's a version 6.0. 6.0 actually does not yet have this. They'll say they'll update that into 6.1. So whenever 6.1 comes out, use that. The main thing here is that you have to have a way to detect errors, artifacts, as well as then either to correct or reject them. Currently in our lab, we're more on the rejection side. Other labs are more on the correction side. And we can debate which ones is better, and that also depends on the application. Yes?
When you say reject, do you mean setting it to 0, setting the 3 letters to 0?
No, in our particular case, we'll just reject the whole DWI. So let's say if we acquire 30 DWIs, we'll throw one out. Now we only have 29. But because we anyway have an overdetermined system for a tensor analysis where we only need 6, if you lose one, that's okay. Now, of course, if you lose half of your data, that's no longer okay. But of course, if you would reject half of your data, trying to correct it is maybe not the best thing either.
Do you do, I'm thinking to like analogies with EEG. So if you rejected it for one participant, would you need to then reject it across, or would you have no problem?
No, I mean, that's where the SNR comes in. So you can't reject too many of them, because otherwise the SNR settings across different subjects is going to be different. So that's why you want to have kind of like a limit on the amount of rejection. And there's later on some more slides about it's not just that, it's also about which gradients are being rejected. So if those gradients of rejections may be correlated, you may be now not sampling a whole part of your diffusion space. And as soon as that happens, the whole image becomes bad. Now, and again, this correction, there's multiple ways how to correct this. If we do this correction on the tensor level, that's probably an okay thing to do, because here we're trying, basically giving the data what's the best tensor that fits the data, knowing these and these data sets are either artifact-rich or outliers. That's what's done in Turquoise, which is an NIH tool specifically used for that kind of robust tensor estimation. FSL does it a little bit different, also because they're not necessarily going for tensors, they're going for higher order models, particularly in tractography, probabilistic tractography. And there, the only thing, what is nice is to detect bad data and trying to correct them is really done nice in FSL, because it doesn't use a lot of assumptions as a Gaussian process-based assumption. But as I mentioned before, if we have lots of error-rich data, meaning if our data is actually really not that good, FSL will give you an answer and will not even tell you that the data is not good. And because of the correction process, it even looks rather artifact-free. Because of that correction, it's not going to look noisy. And because of that, you can sometimes get the impression that your data is good when it actually underneath it is not that good. So it does put out also information of which areas are, so to say, error prone. And that information is probably something that people have to start looking at when they do this new type of FSL analysis. It also gives you a point towards, you may want to not just look at the tensor or whichever fiber model you're fitting locally, but actually look at the raw data. The problem is modern sequences have like 150 or even 200 directions. Now what you're going to be doing, looking at 200 images for every subject. You may have like 100 subjects in your study. So that's a lot of things. And those images are noisy. So it's sometimes not even easier for a human to decide whether an image is good or bad. But yes, so if you can, look at the raw data. It takes some getting used to how they look like. Look at lots of them. The major artifacts that we see are kind of like visualized here. You have these artifacts that look like this, which are motion artifacts in the axial or in the sagittal. You see that if you have if you have an axial acquisition, what you'll see is these Venetian blind artifacts, where it looks like as if it's blind, kind of like goes back and forth. That's a typical motion artifact. Things like here where you have individual slices that suddenly get bright or suddenly get dark, those can be pulsatile artifacts. Those are particularly nasty to take out. And then you rarely see something where, if you look at the diffusion weighted images, they all look all good, but then when you go to the FA image, it just looks wrong. Like in this case here, I'm not quite sure you can see this, it's all kind of like reddish. See if it has this bias towards left-right. And this happens if there's something wrong, either with the scanner. For example, the scanner electronics can be off, or the gradient, one of the gradients may not work perfectly. Or in this particular case, this was a vibration artifact where the sequence, so diffusion sequences are rather rough sequences. They are gradient echo. They really shake the scanner. So the scanner shakes and is very loud. But in this particular case, the patient bed started shaking with the scanner at the same frequency. So there was some resonance to the shaking of the patient bed. And it only happened at certain weights of the baby's being imaged. So this was only being seen in certain studies. This was actually, for a while, the Siemens Tim Trio had that issue and invalidated quite a number of our data sets for a while. And when you have this data, there's no way to correct it. It's crap. You can just throw it away, unfortunately. Now, what if you don't do a QC? Well, you still see a lot of data sets not being well QC'd. And in particular, when your data is not very high signal to noise. So this is a relatively old paper from 2006, where they look at minimally conscious folks, and they want to see whether something is happening longitudinally with certain subjects. These guys, this is a very, very high impact journal. This is a journal of clinical investigation, JCI, anyway, high impact. But what they did here, this is, by the way, not my slide, I got this from Carlo Pierpoli, is basically they looked at signal where there is no white matter. And you see these really high FA areas where it's in the gray matter. That is not, that's just artifacts. There's nothing there. And just because they didn't do a QC, if you look at the individual DWIs, which we cannot do because we don't have them here, this is the only thing that was in the paper. From this, we can follow something that is going on. This is not correct data. We don't see a lot of this anymore, but still, if I see a paper even done on lots of subjects and they're not describing the way their QC is done, I know no QC has been done. And you know, if you are not familiar with diffusion imaging, you just trust FSL, you press that button, and particularly the pre-512, there was simply no QC done. The only thing that was corrected was motion. And if you had data that looked like this, this would be used for estimating your tensor. Now, if you have, 40 directions and you have one of them looking like this, all the other 39 helped out. But if you have 10 looking like this, now you have a significant bias. Or if you only have 12 directions, which is still going on, one like this is going to make, that's like nearly 10% of your signal. So yeah, so QC important. Sorry if I'm being repetitive here. This is one of my last slides. Also, one thing that I mentioned, like if we reject data or that we can potentially not sample some area of the diffusion very well. Another way that can be done is if you don't design your protocol very well. So what you see, this is, for example, the protocol we were using in our Conti study. It's a 42-direction protocol, one B-value, one shell, very nicely distributed. This is kind of like what used to be done of like 10, 15 years ago. This is the 6-directional sequences, which you don't see nowadays anymore, where we just assumed, all right, 6 directions enough, let's get those. But at least this was done uniformly. And this is a Philips scanner sequence that we observed in a study on Huntington's disease. And this is actually comes with the scanner. This is the sequence that comes with the scanner. That was like 15 years ago, but they ran their whole study with this sequence here. And we have to tell them that's a crappy sequence.
Why did they choose that? Did they just not think?
They didn't know. So these was the visualization tools that you see here. People don't have them available. I think FSL has now a way to visualize that, but that's pretty recent. We have a tool that's called DTR Prep that can visualize it. And if you have a little bit of programming skills, you can easily visualize this. It's not hard. But if you never actually look at it, then you have a problem. So whenever you start a new study and somebody tells you, I have this new protocol, let me try it out, go and look at the directions. Make sure that they're good. Usually they're good. And what you can see here, down here, is we did through Monte Carlo studies. What does that mean for your error now when you have these non-uniform distributions of the gradients? What happens is that your error is now not uniform, meaning this is, for example, the error on the principal direction. Very important for when you're doing tractography. Across the whole sphere, with this protocol, the error is around 8% everywhere. So there's the basic error. Depending on your SNR, you go up in SNR, obviously that error goes down. But at the same SNR, that's about the error you see. For this sequence here, in certain areas, that error doesn't nearly double, but it goes, to 14%. And that means that if there's a tract that runs in those directions, those tracks will have higher errors for their tractography than tracks that run in this direction. And you can see, even though here, this one here has less directions, because they're uniform, and obviously SNR is being the same, this is actually better. So more directions is not necessarily good. Yes?
Is it useful to take repeated images in single gradient directions? So you've got 42 directions. I took 84 images and just copied the protocol. Is that useful, or should I shift the
You should
protocol
always
around?
shift.
Okay.
Always shift. So when I say here the 6-direction protocol, what we used to do is we used to do 5 of this. But because you wouldn't gain anything, you wouldn't fill in any in between, it still wasn't that great. So what you want to do is, no, you don't want to have 5 times 6 directions, but you want to have a 30-direction protocol that fills in the full sphere. Just to drive home the point, this is the FA estimation where it goes from like a 0.5% error to triple that error on this particular case. So where, let's say if you have a track that runs like this versus a track that runs like this, you triple the error on the estimation of the FA. So that's why you don't want to make this. The reason is not just that your error is now different for different tracks, it becomes different for different orientations in the scanner. So if you have, let's say, one set of subject that have their head like this, versus another set of subject that has it like this, you'll find a difference just because of that. So that's why you really don't want to have, make sure you don't have a non-uniform protocol. But it also means when you reject data that you don't end up with something like this. So if I recheck, let's say, 10 directions, I don't want to have to just recheck all of them the same place so that they would be correlated. Then we end up in the same situation. Unfortunately, we do not check for that right now. Our tools do not check for that right now. But what is the case, if you do your number of allowed rejected directions to be relatively low, you're basically guaranteed not to end up on those situations. Right. Yes, and so let me quickly see, is this a good breaking point? Now it would go over to tractography, and since we are at 11:05, I think we're going to continue on Thursday with this. Any questions right now on just the tensors? So connectivity is going to be, we're going to extrapolate from the tensors. Right now what we've done is we looked at a per voxel way of what the tensor means and what maps we can get, etc.
How long does the 42 diffusion gradient protocol take?
Well, we did that on the TIM trio, and if I remember correct, it was around 8 minutes.
Okay.
But so that p-value that I mentioned at the beginning, it captures diffusion time and gradient strength. Mm-hmm. So now on the Prisma, we have double the gradient strength. So to acquire the same image at b equals 1000, we basically need half the time. Okay. Think of it like this. So gradient strength is one thing that really impacts this, which is why those really sophisticated sequences that we currently use in the baby connectome, yeah, we can do them on the Prisma. If you take those and try to do them on the TIM trio, which we tried, it's just way too long. It becomes non-feasible. Right. Next one is Thursday. Next Thursday, and I haven't yet decided on the next week, but probably going to be one more next week. And I have most of your schedules, at least those you guys send it to me. All right. Thanks, everyone.
Thank you.
Thank you. Thank you.
So this is the human neuroimaging group, is that right? Or